This recording shows some more background and more information on the sections from Chapter 9 on the central limit theorem. So in Chapter 9, we encounter another central limit theorem, but this time instead of for sample proportions, it's for sample means. And what it says is that under certain conditions, again, there are several conditions, but the only one that we need to check for our class is the one that assures normality. So you have to show that either the sample size is greater than or equal to 25, or the population is normal. And if one or both of those conditions is true, then what we know is that the sample means will have this shape. The center will be the same as the population mean, and the spread, or the standard deviation of the sampling distribution, which we call the standard error, is computed by taking the population standard deviation and dividing by the square root of n. So let me just remind you about these symbols. This is the population mean, and this is the population standard deviation, and this is the sample size. And you can use the CLT for sample means to answer three kinds of questions in exactly the same way you can do this with sample proportions. The first thing you can do is you can describe the sampling distribution. The second thing you can do is you can determine if a sample is unusual. And the third thing you can do is find probabilities involving sample means. Now, something new comes up with sample means that doesn't come up with sample proportions. And I think this is why some of you were having trouble on the section 9.1, 9.2 homework. When you go to StatCrunch and you want to do a problem involving the central limit theorem or probabilities involving sample proportions, you have to be really careful whether you're talking about the standard deviation of the sampling distribution, which is this formula here, or just this standard deviation of the sample. So you have to be careful about that. Let's do some examples. Women's heights are normally distributed with a mean of 65 inches and a standard deviation of 2.5 inches. Find the probability that a randomly selected woman is taller than 67 inches. To do this problem, we don't need the central limit theorem. This is a problem that we could have done from Chapter 6. I think it's in Section 6.2, if not 6.2, 6.3, because we're not taking a sample of women, we're just taking one woman, a randomly selected woman. And to do this problem, you would simply say, okay, heights are normally distributed, the mean is 65 inches, the standard deviation is 2.5 inches, here's 67 inches, and I'm being asked to find this area, which corresponds with the probability. I'll do that just using my normal calculator. And so you would simply go to the normal calculator. So stat calculator normal. And you would enter the information. So the mean is 65. The standard deviation is 2.5. And you're interested in the probability that a woman is taller than, I'm not sure what we said in the problem. Let me go back and check for a moment. You're interested in the probability that the woman is taller than 67 inches. And so we want to know the probability of a number greater than 67, and that's 21.2%. All right, so this would simply be equal to 21.2% because when we went to StatCrunch, in this box where it said standard deviation, This was the picture we were looking at, and the standard deviation was 2.5 inches. However, you have to be careful when you apply the central limit theorem. So let's take a look at this example. Suppose we take a sample of 10 women and we find their mean height. Can we find the probability that the sample mean is greater than 67 inches? If so, find it. If not, explain why not. So here's a question involving a sample mean, and so the question is, can we use a CLT? Well, remember that to use the CLT, either n has to be greater than 25 or the population has to be normal. Well, if you look back here, well, first look here, the sample is 10, so the sample size is not greater than 25, but if you look back in the original problem, we're told that the population of women's heights is approximately normal. So since one of these is satisfied, the answer is yes, we can find the probability. So let's start by drawing a picture. So what does the central limit theorem tell us? The central limit theorem tells us that the sample means will have a normal distribution. They'll be centered at the population mean, but the spread, which we call the standard error, is sigma over the square root of n. So the standard deviation of this distribution, which is not the same as the parent population distribution, is 2.5 divided by the square root of 10, and 2.5 divided by the square root of 10 is about 0.79. So this distribution has a spread which is narrower than the first one that we looked at. But we would answer the question in the same way. Here's 67 inches. We want to find this area, but the standard deviation of this distribution is 0.79. So in a moment, when we go to StatCrunch, and it asks us here for the standard deviation, we have to remember that we're doing the standard deviation of the sampling distribution. And so we've had to apply this formula. And so in this box, we're putting 0.79, not 2.5. So you have to be really careful about what kind of distribution you're looking at. That's why I always draw a picture before I go to StatCrunch. Okay? And so if you're having trouble with the homework, that's probably why you're getting them wrong. So let's go ahead and give that a try. So notice everything is the same, but the standard deviation of this distribution is not 2.5, it's 0.79. But we're still looking for the probability of something greater, a mean greater than 67 inches. And that goes all the way down to 0.5%, 0.6%. Let's talk about why that's true. So this is equal to 0.6%, 0.006. So what that says is that it's very, very unusual to take a sample of 10 women and have an average height greater than 67 inches. Why is that true? Well, back here, the probability of one woman being pretty tall, above 5'7", is 21%. But in order to have 10 women have an average height greater than 5'7", that means they all had to be pretty tall. And what are the chances of getting 10 pretty tall women in a random sample of 10 women? Well, in a random sample of 10 women, some might be tall, but some you should probably have some short ones in there too, right, to balance things out. So if we really did have a sample mean that was greater than 67 inches, that means that most of those women had to be taller than the average woman, and the probability of that happening is rather small. Let's see what happens if we increase the sample size. Suppose we take a sample of 40 women and find their mean height. Can we find the probability the sample mean is greater than 67? If so, find it. If not, explain why not. Okay, so again, you have to either show that n is greater than 25 or the population is normal. In this case, both of these things are true. The population is the sample size is greater than 25. The population also happens to be normal. Again, not both of these have to be true, but you have to have at least one of them true in order to proceed. If neither of them was true, you had to stop. All right, so what does that mean? What do these happy faces mean? That means we can apply the central limit theorem. The sample means will have this kind of distribution. They're going to be centered at the population mean, and we can figure out their spread or their standard deviation. It's going to be equal to 2.5, but this time divide it by the square root of 40. And this is even smaller than before. 2.5 divided by the square root of 40 comes out to be 0.40. So again, same question, still looking for this area. All right, so now let's go ahead and see what happens if we change that standard deviation. So now our picture doesn't have this standard deviation. Now the standard deviation is 0.40. Otherwise, same information, same mean, still looking for the probability that x is greater than 67. Look at the change in the probability. You don't even see any red shading. That means this is almost close to 0, approximately 0. So this one actually comes out to be around 0. It's even less than before. The one before was pretty close to 0. This is even smaller than that. Well, why is that true? Well, if you take a sample of 40 women and their average height is over 5'7", that means almost all of those 40 women had to be tall. What are the chances of getting 40 tall women in a sample of women? It's less than the probability of getting 10 tall women in a sample of women. So we can see that the probability here went down close to 0 from pretty close to 0. But the probability of one tall woman is about 21%. So again, if you're having trouble with this homework, you have to be very careful about what number you put in for the standard deviation. That's why you never should go to StatCrunch unless you have a picture and you know exactly what you want to compute using StatCrunch. If you just open StatCrunch, you'll be tempted to put 2.5 in this box when you're really needing the standard deviation of your sampling distribution. So just be careful. One last problem. How would this problem be different if we remove the phrase approximately normally distributed? So if we had the same problem, pardon me, but we took out this phrase, this just wasn't there in the beginning. It just said women's heights have a mean of 65 inches and a standard deviation of 2.5. How would this be different? Well, we could not have done this problem. Why? Because we could not have drawn this picture. This picture is based on a normal distribution, so we could not have done the first problem. We could not have done the second problem because the sample size was too small to apply the central limit theorem, so we could not have done this problem either if we took the phrase normally distributed out of the problem. However, we could have done this problem because our sample size would have been large enough. So even if we did not have the phrase normally distributed in the problem, we could have still done problem 3, but we could not have done any of the others. So that's a little more recap on the central limit theorem for sample means. And again, the reason why you might have had trouble on that homework is you have to be really thoughtful about what are you going to put in that box called the standard deviation. And you might be wondering, well, why doesn't StatCrunch tell me I need the standard error instead of the standard deviation? Well, it's a computer. It has a template, right? So you have to know what standard deviation you need. And the way you know what standard deviation you need is by taking the time to think about the problem and draw a picture of it before you start trying to do it on the computer. Okay? So that's a quick recap of the central limit theorem for sample means.